Thank you very much, Farcine. First, I would like to thank Peer, their kind invitation, Farcine, to organize this. And I must say that I'm wearing my blue and gold tie. I'm probably going to be blackmailed next week in class. But I actually lived in International House when I was a student here many years ago. So a lot of the stuff that I'll be presenting, it's thanks to the instrumentation of CSMIP and USGS, and a lot of the work is been done by one of my former PhD students who's now a professor in Chile. Just before I get into the topic of the presentation, I wanted to share with you, related to what was discussed this morning, what we were doing last week. And of course, these earthquakes never send us a memo to get prepared, but we had the opportunity to represent Pierre, Steer, and the Bloom Center over there and try to gather a lot of data, and there you see a little bit of what we were doing. And in particular, one of the things that got me interested in going over there was the availability of a fairly good network that they have over there, and including some instrumented buildings. So it's really this kind of things that I've been doing for a number of years and learning and try to create what I recall, I refer to as data motion pairs that allow us to improve what we do in design. So all of this is really only possible. There are a lot of earthquakes, but our learning opportunities are very limited if we don't have instrumentation. So it's really instrumented buildings, instrumented structures, and ground motion stations that allow us really to maximize that learning. So that's why I've been involved in committees, trying to push for instrumentation and then doing more with it. In terms of damping, I got interested in damping many years ago, and I continue to be interested because it's an area where I think we don't know a lot. And even though we started doing this long time ago, this is an image of some studies that were done at Stanford by Professor Lydic Jacobson many years ago with a young student named John Bloom. And that continued with at Caltech by Professor Hausner and his colleagues, and what was, at least that I know of, the first system ID in one of the aftershocks of the Long Beach earthquake in 1951. So in terms of getting into this area, I tell students that we learn and do research by posing ourselves some questions, and this is a sample of the kind of questions that I pose myself related to damping. And the idea is to see if seismic instrumentation and structures that are instrumented will allow us to improve and answer at least some of these questions the best possible. So I'll go very fast. I don't have a lot of time, but tell you a little bit about what we've learned over the years in this respect. In this respect, I found that there's a number of misconceptions related to damping, perhaps more than other areas of earthquake engineering. As you all know, Nigel Priestley wrote a famous paper called The Myths and Fallacies in Earthquake Engineering. He revisited. That's the cover that I'm showing over there. And sometimes when working on damping, I feel like I'm following his steps. I happen to follow him actually when we were once climbing in the Alps, and that's Nigel over there, and trying to keep up with him. He was a great climber, and I didn't know that and had the opportunity to do that. The first day we had a 1,000 meter elevation and I couldn't keep up with him. And so sometimes I say, somebody's got to write a paper called The Myths and Fallacies related to damping. So I'll tell you a little bit about what I've learned in that. The first one is that somehow there's a dichotomy in terms of the damping of some of these structures that is different for wind and seismic loading. And this is, some older recommendations, but of course the wind community uses values like 1 or 1.5% and sometimes less than that. Whereas the earthquake community, we sort of, came up with this magic 5%. And if you actually go into the literature, and I encourage you to do that, to actually keep track of where the 5% came, you will see that it's a very interesting myth. And so obviously, don't believe me, just think about why would it be different, the energy dissipation mechanisms on one of these buildings, whether you shake it at the base or you push it with wind And we're finding that there's a lot more similarities with the wind community. So in the first generation of the TBI peer guidelines for tall buildings, for example, we would recommend a value of 2.5%. And even with stuff that I had done like 12 or 15 years ago, I said, you know, I don't think that 2.5% it's correct. And this is some of the older studies that had looked, some of these high-rise buildings here in San Francisco and some in Los Angeles, and trying to learn about how they move during earthquakes. These are some examples of the instrumentation. And I won't go into the details, but basically what we do is system identification, and we have our structure. This is sort of like the cover of Professor Chopra's book. We get a ground motion, we record some motions at different levels, and then we try to come up with simplified models and models that will try to reproduce the recorded response to learn about some of these dynamic properties on the building. And so we're using time domain parametric system identification, which is essentially an optimization function, trying to minimize the difference between recorded and computed response. But perhaps more interesting, this is just one example of a 52-story building downtown Los Angeles, in which I'm comparing the recorded and computed response. And you can see that, you know, you can match it fairly well. You almost cannot distinguish one from the other. But what is interesting about these high-rise buildings, there you see the ground motion in the bottom, and look at how short duration motion, and that's Northridge, and then just look at all the movement that is going on in the different levels of the building, and they go on for a long time. And actually here I'm only showing 3 minutes of record, whereas, you know, sort of this significant durations for that record, it's only 15 seconds. And so we compute also accelerations along the height, floor spectra, and these kind of things. But then we say, well, what are the dynamic properties that we're requiring these models to match the recorded response that we could improve what we do when we're designing or seismically evaluating what these buildings are? So these are some of the dynamic properties that we identify. So pairs of vibration, damping ratios, and then gamma phase or effective mode shapes. And we do this in a series of earthquakes. And here I'm just showing, you know, how, as we know, of course, the periods get shorter with a mode number. But perhaps not as well known is that the damping increases with higher modes. And a lot of people in the literature, if you look, and I'm kind of an odd person that I like to read a lot and really old papers and stuff. And if you read this, almost, you know, very commonly people say, you know, I would not like to overdamp higher modes because I may underestimate the response. But if you actually look at what is going on in the structures, we get more damping in these higher modes. And for this particular structure, for example, in this particular earthquake, this particular direction, it's about 1% for the first mode, and it was probably designed for 5%. So you wonder, you know, what level of response would happen, and in this case, even with respect to the first generation of TBI, would be a fairly large difference. And in the first set of buildings that we looked at, there were just 14 tall buildings. As you see there, you know, typically these damping ratios were much lower than that 2.5 that was recommended in these provisions or guidelines, and much closer to what it's used in wind. So we started complete the data set, and here there's a description of what we put together, and then we developed some procedures to just keep what we thought was more reliable data, because it's kind of tough. There are a lot of sort of like issues with damping identification, and then we this is just sort of comparing with what was used in that first generation of TBI, was mainly ATC 72, and we significantly expanded the data set. And this is nothing really new. I mean, there's a number of studies, actually, some of them as old as 50 years, pointing, mainly Japanese investigators, pointing that there was, you know, big influence of the height of the building. And so we did some regression analysis and provided some recommendations to improve those guidelines. And that has been incorporated now in the new peer guidelines for San Francisco, and the same thing for Los Angeles. And I'd like to say, we're at least partially successful in convincing the different committees, at least for the serviceability limit state for the MC, there's still a height independent 2.5% damping. Personally, I don't think that's correct, but maybe I just need to keep working on trying to convince my colleagues about that. This is just one example of how we've looked carefully, whether this is really viscous or not. And we know that it's not truly viscous, but many other studies have shown that with viscous you can actually do a good study. And I don't have a lot of time to go into that, but one of the main reasons why viscous damping works so well is because I believe a lot of the soil structure interaction that takes place in these structures and through radiation damping, that's really what drives this. And Professor Leismer, a Danish professor here at Berkeley many years ago, wrote a famous paper on that you could replace sort of like an absorbing boundary by using viscous dashpots. So that explains very well what's going on. The other sort of myth around this is that there's, what goes on with this amplitude dependence with damping. And of course, this has been observed both for earthquakes and wind for many, many years. This is one example from the Millikan Library where Professor Jennings and his then student Julio Curuilla, a Peruvian, they did some force vibration on Millikan Library on the Caltech campus, and they noticed that amplitude dependence of damping, but it was really tiny, the amplitude that they were able to get with these shaking machines that Jacobson and Bloom first designed. And then we sort of extrapolated this amplitude dependence to much larger. So, the general thinking is that because earthquakes have much larger amplitudes than winds, then, obviously we will get a lot more damping. But actually that extrapolation, we started to see how valid it is. So I'll just show you a few examples of this, but this is a particular building in Los Angeles where we have different earthquakes increasing the amplitude of motion 25 or 32 times, and we see about the same level of damping. And this is another example from that 52-story building, in this case in the order of 20 times more amplitude. And again, the damping is not changing very much. These are others, and people like to say, well, that's really tiny level of motion and so on. I've done a lot of research on partition walls, and I know very well when they start cracking and all those things. And these are peak roof drift ratios. If you look at the peak interstory drift ratio, they're going way above the level in which you start having damage in facades and partition walls and so on. And still, you don't see a lot of increasing damping. This is, similar information that the wind community has done over the years, but now pushing it to much larger levels of deformation. And again, we don't see a lot of amplitude dependence. There is a tiny bit. And I wanted to show you something a little bit what has happened. I've been doing this since I was in Mexico. Mehmet Çelebi from the USGS had compared ambient vibration dampings with strong motion, and this is similar to what was done with periods after the 1971 San Fernando earthquake. We know that they're very different. But I wanted to say, what goes on between an ambient vibration and a strong motion? So I started to look, thanks to the seismicity in Mexico, any little tiny earthquake and so on, and trying to sort of see what goes on in between. And what we're finding, and colleagues at Chile, Rubén Borocek, who's a good friend of mine, was my colleague here at Berkeley when we were doing our PhDs, he's observed the same thing in Chile in a number of buildings. And this is actually, it's also similar to what several people in the wind community has reported. A lot of the change takes place when these buildings are starting just to move, but after that, they tend not to increase a lot of their damping. Another sort of myth that goes on to this, forever, you have these publications by Newmark and Hall. They have a little table and they tell you what are the damping ratios. And there's not really source of where this thing come from. So we try to do sort of like a literature review of where this thing come from. And actually, from some class notes from Professor Clough here from the 60s, we found that he was referring to the best source of information was Stanford, actually, going back to this Danish professor, Lydik Jacobson, who had, of course, developed equivalent linearization. And all of those tests were just component static tests. So they're really not really damping, but that's really where it comes. So, we all think that of course, damping ratios in concrete structures are larger than steel. And here I'm showing you a comparison, but if you now take into account this variation with height, there are actually no statistically significant difference between steel and concrete. And again, wind community has also found some of these things. Another thing, how about the role of the lateral resisting system? We compare, in this case for steel buildings, moment resisting frames with steel braces, and that's what I'm showing you here, a little bit larger damping ratios for moment frames. And again, this is consistent with what Tracy found over at in the high-rise project in Chicago with wind loading. Then we also evaluated the Rayleigh damping, and I'm a big fan of John Strutt, and you can, I tell my students, but I don't know if they're following the advice, but you can download these books from Google Books and read them at night, and they're fascinating. The word damping didn't exist, so it was just dissipative forces he would describe, and how he described what we now know as Rayleigh damping. It's fascinating. But I always thought, it would be a huge coincidence if this great mathematical convenience of damping were to actually be true. So we've been looking into that thing, and what we found, and this is an image that you may have seen in Professor Chopra's book, but it actually comes from a PhD thesis from what I would describe sort of the golden years of Caltech, and into sort of like a physical interpretation of what damping, Rayleigh damping is. And we see, what did this tell us in terms of the variation of damping ratio with frequencies in these buildings? And I'll show you one example. This is in the Sierra Madre earthquake. It's a tiny earthquake near Los Angeles, and what I'm plotting on the vertical axis are damping ratios of the different modes. There you see plotted against the frequency of each one of these modes. And then we do this in different earthquakes. We do have a little bit of earthquake to earthquake variability, but the trend is very clear of increasing this damping ratio with increasing frequency. So we've done some regression. I won't go into that. But I'll show you just very quickly lots of buildings where we've seen this. And other than 2 buildings, every other building in which we've been able to reliably identify damping in higher modes have higher damping ratios in higher modes. So I'll just wrap up with some conclusions. Damping ratios decrease with increasing height. We've known this for 50 years. We just not used it for seismic design, but thanks to this tall buildings performance-based guidelines, we will now start doing this. And then, as I mentioned, there's a lot of similarities of our results with those of the wind community. And there is amplitude dependence, and it can actually be fairly important, but it occurs at really tiny levels of deformation, and beyond that, there doesn't appear to be a lot of that. Now, of course, once the structures start going nonlinear, if you actually model that nonlinearity with hysteretic damping, you wouldn't duplicate by adding some large equivalent damping. As I mentioned, in terms of the material, we think that there's not a lot of difference between steel and concrete. There are some differences with lateral resisting systems, and those, I believe, they have to do more with soil structure interaction. I didn't have a chance to go into that. But the other thing is that the damping ratios increase approximately linearly, so it's not exactly stiffness proportional, but you do have a linearly increasing damping with frequency. And again, several people in the wind community had suggested that previously, so we're finding that, you know, it's the same building. Why would it be different under if you move the base and you push it on the different facades? We didn't find any evidence of mass proportional damping, so we don't recommend to use it, or you need to modify some things over there. And again, I didn't have a chance to go a lot into soil structure interaction, but I believe it's the major source of this damping in these buildings. And in particular, if you actually look with relatively simple models of SSI, like a uniform half space, you can actually explain why the viscous damping works so well, which again, it all boils down to UC Berkeley and Professor Leismer. I was fortunate enough to have a class on soil dynamics with him, and you know, whenever I'm working, I still sort of hear his voice talking about the frequency domain, and then the reduction in damping ratio, it's also consistent with soil structure interaction, the same thing as increase in damping for the higher modes. And with that, I'll just show you with one image that I took just before heading to Puerto Rico in the Yerba Buena Island with one of my students who also likes photography. That's our next test bed. We're doing a little comparison of how these buildings that you're looking into this image, if you were to model them with 5% damping with what we think would be more realistic levels of damping. Thank you very much.